Welcome to this series on Python 3.15. We will move from the release timeline into the language changes most developers will notice, then examine profiling, observability, runtime performance, typing, the standard library, and the C application programming interface. The final chapter turns those changes into a practical test and migration plan. The feature set is now at release candidate maturity, so the emphasis is on what has been accepted and implemented, while still calling out documentation, tooling support, and benchmark details that may continue to settle before the final release. This chapter starts by locating Python 3.15 in its release cycle, because the word planned means something different after feature freeze. We then focus on the changes closest to ordinary Python code, explicit lazy imports, the new frozen dict and Sentinel built-ins, unpacking inside comprehensions, the switch to UTF-8 by default, and improvements to interpreter feedback. The goal is not merely to learn new syntax. It is to understand the behavioral boundaries, compatibility risks, and testing priorities behind each feature. Python 3.15 entered feature freeze with Beta 1 on May 7, 2026. Release Candidate 1 followed on August 4th. At this stage, the accepted feature set and application binary interface are locked. Only reviewed fixes should land before the final release. Release Candidate 2 is scheduled for September 1st, and the final release for October 1st. For maintainers, this is the practical testing window. Source and binary compatibility can now be evaluated against a stable interface rather than a moving alpha target. The release candidate boundary is useful because it separates two kinds of uncertainty. The feature list, grammar, public interfaces, and binary compatibility target are no longer speculative. What can still change is the quality around those features. Clearer documentation, bug fixes, ecosystem packaging, and benchmark results on additional workloads. Teams should therefore avoid treating Python 3.15 as an idea backlog. It is now a testable release candidate, although broad production adoption should still wait for organizational readiness and dependency support. The most visible application-facing changes share a theme. Python is standardizing patterns that developers already implement by hand. Lazy imports replace scattered inline imports when startup latency matters. Frozen dict supplies an immutable mapping without a third-party dependency. Sentinel standardizes the common need for a value distinct from none. Unpacking comprehensions make flattening and merging read more directly. None of these features requires an all-at-once migration, which makes Python 3.15 suitable for incremental adoption after compatibility is established. A lazy import creates the binding immediately, but postpones loading and executing the target module. The first ordinary use resolves the proxy, performs the import, and replaces the binding with the real object. This keeps imports visible at the top of the file, while avoiding work for code paths that never need them. The trade-off is temporal. Import errors and module side effects move from the import statement to the first use. That shift is often valuable for command line startup, but it must be part of the design rather than an invisible optimization. The operational model has three moments. First, Python records the lazy binding without putting the module in sys.modules. Second, the rest of startup proceeds, potentially without touching that dependency at all. Third, a normal name access resolves the proxy and performs the import. If resolution fails, the enhanced exception chain shows both where the lazy import was declared and where it was first used. This model improves startup only when the deferred path is genuinely optional. A dependency used immediately simply moves the same work a few lines later. The design deliberately avoids making all imports lazy by default. The new syntax is valid only at module scope and does not apply inside functions, classes, or try blocks. Star imports and future imports cannot be lazy. Normal imports retain their historical behavior, unless a module-level compatibility mechanism or an advanced global policy selects them. These restrictions preserve local reasoning. A reader can normally see the change at the import site. They also reduce the risk that error handling written around an eager import silently stops working. The compatibility bridge is a module global named _lazy_modules__. It lists fully qualified module names whose otherwise ordinary imports should become potentially lazy on Python 3.15. Older Python versions parse the file normally and ignore the variable, so one source tree can support both behaviors. This is especially useful while a package still supports 3.14. It should not become a hidden dumping ground. Record why each dependency is deferred, test import time side effects, and prefer the explicit keyword once the project can require Python 3.15. Frozen dict is a new built-in immutable mapping. It is not a subclass of dict, but it implements the standard mapping protocol and offers familiar construction, iteration, equality, and merge behavior. Insertion order is preserved for iteration, while equality and the hash are based on items rather than order. This makes the type useful for cache keys, set members, and safe defaults when its contents are fully hashable. Code that insists on isInstance, value, dict, may need to accept mapping or explicitly include frozen dict. The frozen boundary applies to the mapping structure, not recursively to every referenced object. A list stored as a value can still be appended to, and that also makes the frozen dict unhashable. Construction from a dict performs a shallow copy, so later key changes to the source dict do not alter the frozen dict, but shared nested values can still be observed. This distinction matters for security and concurrency discussions. Frozen dict prevents accidental rebinding, yet it is not a general deep freeze facility or a substitute for careful ownership of nested mutable state. Sentinels are for APIs where none is a meaningful value, and omission must be represented separately. The built-in Sentinel factory creates a unique object with a concise name. Identity check's use is making intent explicit and avoiding accidental equality behavior. Python 3.15 also lets the Sentinel value participate directly in a union type, so the runtime default and the static signature describe the same state model. This replaces many private object instances and one-member enumerations with a standard, discoverable idiom. A useful Sentinel needs more than uniqueness. Its representation should explain itself in logs and signatures. Copying should not manufacture a different marker. Serialization should restore the intended identity when the Sentinel is importable from its module. Static typing should distinguish the marker from valid domain values. The new built-in is designed around all four requirements. Libraries should still define Sentinels at module scope, give them stable names, and avoid creating fresh Sentinels inside a function where identity and pickling become harder to reason about. PEP 798 extends the unpacking vocabulary developers already know from list, set, and dictionary displays. A starred expression at the front of a comprehension emits the members of each produced iterable. For a list of lists, the result is a single flat list. The older double loop form remains valid and can be clearer when additional filtering or transformation is needed. The new form is strongest when the job is simply to combine an arbitrary number of existing iterables without introducing another function or reversing the natural reading order of the loops. The same grammar applies across collection kinds. In a set comprehension, starred iterables contribute their members to the set. In a dictionary comprehension, double-starred mappings contribute key-value pairs, with later values winning for repeated keys just as in ordinary dictionary unpacking. A starred generator expression delegates the values from each produced iterable without first creating the full combined collection. Reviewers should still choose the spelling that makes data flow clearest. Concise syntax is useful only when the unpacking behavior is immediately apparent. Python 3.15 enables UTF-8 mode by default, making implicit text encoding consistent across common environments. The change mainly affects systems that previously used a non-UTF-8 locale, especially Windows installations and integrations with legacy files or processes. It does not mean every text file is UTF-8. It means omission now expresses a different default. Code that intentionally consumes locale encoded data should say encoding equals locale. Code that owns a UTF-8 format should continue to state UTF-8 explicitly, so its contract remains clear across Python versions and tools. The migration strategy is to turn hidden assumptions into explicit contracts. Run tests with the optional encoding warning to find file operations that omit an encoding. Decide whether each file belongs to a UTF-8 format, a locale-defined integration, or a binary protocol. Then test both with UTF-8 mode disabled and with the new default. This catches decoding errors, mojibake, and silent corruption before deployment. Explicit UTF-8 remains valuable even though it matches the new default, because the code then communicates ownership of the format rather than reliance on process configuration. Python 3.15 continues the trend of turning failures into more actionable feedback. Attribute errors can suggest that the requested attribute exists on a contained member, while failed deletion can suggest a close spelling. Color expands across help, command line tools, completion, and unraisable exceptions. These changes do not alter program semantics, but they can affect snapshot tests and log parsers that compare terminal output exactly. Automation should disable color or normalize output when stable machine-readable text matters, while interactive use can benefit from the richer visual cues. A focused compatibility pass can cover most application-level risk. For imports, identify modules whose initialization performs registration, logging, or environment checks. For mapping APIs, replace unnecessary dict-only checks with the mapping protocol, and test whether callers expect mutability. For text, exercise non-UTF-8 inputs and subprocess boundaries. For tooling, verify that formatters, linters, syntax highlighters, test collectors, and code generators understand the new grammar. These checks are more valuable than adopting every new feature immediately. These official sources define the release date and the application-facing features covered in this chapter. The release schedule and candidate announcement establish the freeze and final release dates. The What's New document is the integrated implementation summary. Each Python enhancement proposal provides the normative design, compatibility reasoning, and detailed semantics for its feature. Because the release documentation remains a draft until final, revisit the What's New page when Candidate 2 and the final release are published. The language-level story is not novelty for its own sake. Each major change makes an existing intention easier to state. Lazy imports say when work may be deferred. FrozenDict says a mapping structure must not be rebound. Sentinel says omission is a distinct state. Starred comprehensions say that the desired operation is flattening or merging. UTF-8 mode removes an environmental default, while explicit encodings still document ownership. The next chapter follows the same principle into performance. Measure the system clearly before deciding how to optimize it. Python 3.15 pairs runtime. Work with a more coherent way to observe it. The new profiling package brings tracing and statistical sampling under one namespace. Frame pointers are enabled by default, so native profilers can see Python frames more reliably. The experimental just-in-time compiler gains a tracing front-end and better code generation, while selected interpreters, codecs, allocators, and garbage collection paths change underneath applications. This chapter separates measurement capabilities that are ready to use from performance results that still depend heavily on platform and workload. The safest headline for runtime work is improved visibility. A benchmark percentage can change with compiler flags, processor architecture, or the benchmark suite. A better profiler changes how teams find bottlenecks on their own workloads. Python 3.15 therefore deserves two separate evaluations. First, validate the new profiling and native stack workflows in development and staging. Second, benchmark the available runtime configurations against representative traffic. Treat published speedups as evidence that testing is worthwhile, not as a capacity planning promise. The new profiling package organizes two complementary techniques. Tracing records events such as calls and returns, and is useful when exact call relationships matter. Sampling periodically observes stacks and usually imposes less distortion on long-running processes. The sampling implementation is named Tachyon and supports formats used by common analysis tools. The older profile module is deprecated with removal planned for Python 3.17, so tooling maintainers should begin moving integrations toward profiling.tracing rather than adding new dependencies on the legacy namespace. Sampling and tracing answer different questions. Sampling is usually the first choice for a long-running service because it can observe a process without instrumenting every event. Its statistical model can miss brief or rare work. Tracing records a fuller event stream, which helps reconstruct exact call relationships, but can change timing and generate much more data. A useful workflow starts with sampling to identify a region, then applies tracing or targeted instrumentation to the smaller area where precise causality matters. The sampling command line interface is designed for operational use. It can attach to a running process, sample for a defined interval, and write a chosen format. That separation is valuable. Collection can remain lightweight on the target host, while visualization happens elsewhere. Exact permissions and process access rules still depend on the operating system. Before relying on the workflow in an incident, exercise it on the same container, service manager, and security profile used in production. A profiler is most useful when it fits the operational moment. Attaching helps with a service that is already slow. Launching under the profiler captures startup and import work. Aggregation makes repeated stack patterns easier to interpret and keeps output manageable. Export lets teams compare runs or use established viewers. These modes also suggest a test plan. Confirm that startup, steady-state load, and an intentionally stressed scenario each produce data that an engineer can interpret without special knowledge of the profiler internals. No single output is best for every audience. Console summaries support a quick local question. JSON supports automated comparisons, provided the schema and collection settings are controlled. Collapsed stacks feed FlameGraph workflows. Speedscope files support interactive exploration and can be shared with reviewers. Standardize one format for routine regression work and retain another for exploratory analysis. Always record sampling frequency, duration, Python build, and workload alongside the profile so later comparisons remain meaningful. PEPEP 831 enables frame pointers in default builds. This improves stack unwinding for system profilers, particularly when a hot path crosses between Python, the interpreter, and extension code. The change does not replace Python-aware profiling. It makes native tools more informative. Frame pointers consume a register and can have a small performance cost, so benchmark-sensitive environments should measure it. For most teams, the observability gain is the more important default because it reduces the need for a special diagnostic build during an incident. The practical value of frame pointers is continuity. A service may enter a Python function, cross into a compression or database extension, and spend most of its time in native code. If stack unwinding loses the caller, engineers see a hot native symbol without knowing which Python request path reached it. With a connected stack, the same sample can show application context, interpreter frames, and native work. That shortens the path from symptom to an actionable owner. The experimental just-in-time compiler gains a tracing front-end. Instead of compiling an entire function in isolation, it follows a frequently executed path and specializes that path using observed information. Guards protect the assumptions used by generated code, while exits and exceptional paths return safely to the interpreter. LLVM21 is a build time dependency rather than a deployment time requirement. This remains an experimental configuration, so evaluate correctness, debuggability, build reproducibility, and warm-up behavior alongside speed. Basic register allocation is an important step from a working compiler toward useful generated code. Keeping frequently used values in registers reduces memory traffic and creates more opportunities to avoid redundant reference count operations. The implementation is still described as basic, which is a reminder that future releases may change both results and trade-offs. When testing, include code with loops, object operations, branches, and exceptions, rather than relying only on numeric micro-benchmarks. Python 3.15 does not add one isolated JIT optimization. It strengthens each stage, collecting traces, representing more operations, simplifying work, assigning registers, generating machine code, and returning through exceptional control flow. That broader coverage matters because a fast, happy path is not enough for real applications. The remaining uncertainty is workload coverage. A trace that contains unsupported behavior can still fall back to the interpreter, so profile which functions actually compile and how often guards fail. The Python 3.15 documentation reports an 8 to 9% geometric mean improvement over the optimized standard interpreter on x86-64 Linux, and 12 to 13% over the tail calling interpreter on ARch64 macOS. The chart uses the midpoint only to visualize those ranges. The documentation also says the benchmark results are not final, and that individual benchmarks vary widely. Use these numbers to justify an experiment, never to forecast a universal reduction in compute cost. Official Windows x64 binaries use the tail calling interpreter when built with Microsoft Visual C++ 18. The What's New document reports a 15 to 20% geometric mean improvement, with individual workloads ranging from 14 to 40%. These are observed results for that interpreter and build combination, not a language guarantee. Windows-heavy organizations should benchmark the official candidate binaries because the change can materially affect throughput, latency, and the validity of baselines collected on earlier Python versions. The standard library codec work is unusually large. The documentation describes base 64 encoding as roughly twice as fast and decoding as roughly 3 times as fast. Base 85, ASCII 85, Z85, and base 32 operations are described as about 2 orders of magnitude faster. The 100 times bars are therefore a visualization of that phrase, not an exact benchmark result. Applications that spend meaningful CPU time on encoding should retest end-to-end performance, because allocation, input sizes, and surrounding I/O can change the realized gain. Python 3.15 uses Mimolock for default raw allocation in free-threaded builds. An allocator can change contention, fragmentation, memory footprint, and latency, even when application code is untouched. The effect is especially relevant to extension modules that intercept or make assumptions about allocation behavior. Compare standard and free-threaded builds under the same concurrency and object lifetime patterns. Record both throughput and resident memory, since an allocator improvement in one dimension can have a cost in another. The generational garbage collector was restored after reports that the newer incremental approach created memory pressure in real applications. The restoration appears in Python 3.14.5 and the 3.15 release line. This is a useful reminder that memory behavior is workload dependent and may not be visible in short CPU benchmarks. Exercise long-lived processes with realistic caches, cycles, request bursts, and idle periods. Compare peak and steady-state memory, collection pauses, and object retention patterns before changing thresholds. A credible evaluation varies one dimension at a time. Record the exact Python build and whether it uses the standard interpreter, tail calls, the JIT, or free threading. Test the platforms that matter, because compiler and architecture influence results. Include startup, steady state, burst, and extension-heavy workloads. Capture throughput and latency together with profiles, memory, and errors. A configuration is ready only when its improvement is repeatable and its operational behavior remains understandable. These official documents cover the measurement and runtime changes in this chapter. The What's New document provides the integrated implementation and performance summary, including the provisional benchmark ranges. PEP 799 explains the profiling namespace and migration from the older profile module. The profiling library pages describe tracing, sampling, tachyon, commands, and output formats. PEP 831 gives the rationale and trade-offs for enabling frame pointers. Recheck the integrated documentation after the final release for any benchmark or command line refinements. Python 3.15 provides a better sequence for performance work. First, make the system observable through sampling, tracing, and connected native stacks. Next, establish a representative workload and baseline. Then compare interpreter, JIT, allocator, and free-threaded configurations while monitoring memory and failure behavior. This order keeps acceleration evidence-based and preserves debuggability. The final chapter turns to the ecosystem boundary, typing, standard library APIs, package startup, extension compatibility, and the migration work required around them. Python 3.15 reaches beyond syntax and runtime performance. The typing system can describe type forms, closed typed dictionaries, and disjoint class hierarchies. The standard library adds integer-specific mathematics, Unicode 17 support, grapheme iteration, TOML 1.1, and new concurrency and security controls. Package startup moves toward explicit start files. The C interface gains a free-threaded stable ABI and several safer construction APIs. This chapter explains those surfaces and closes with a staged readiness program for applications, libraries, build systems, and extensions. The ecosystem changes are best understood as contracts. Typing features let libraries state more precise static expectations. Standard library additions establish shared implementations for previously external or handwritten behavior. Package startup gains a clearer, executable boundary. Native extensions receive an ABI target for free-threaded Python and APIs designed to reduce fragile structure access. Each contract can improve portability, but only if code generators, type checkers, packaging tools, and build systems understand it. PEP 747, PEP 728, and PEP 800 target different sources of ambiguity. Typeform describes a runtime value that represents a type expression. Closed typed dictionaries distinguish an exact schema from an open one, while extra items describe the type of remaining keys. The disjoint base decorator lets a class family state that unrelated subclasses cannot overlap. Runtime behavior changes little. The benefit depends on type checker adoption and on library annotations that use the features accurately. Typeform fills a long-standing annotation gap. Some APIs accept a runtime value that is itself a type expression, including parameterized forms such as list of int. Annotating that value as type or object loses information. Typeform keeps the represented type available to the type checker. The exact runtime interpretation still belongs to the receiving library, so implementations must document which typeforms they accept and how they handle constructs that cannot be tested directly with this instance. Typed dictionaries previously behaved as structurally open mappings, which made it hard to express exact object shapes or uniform extension fields. A closed typed dictionary says no other keys are valid. Extra items keep the mapping open but constrain every unspecified value to one type. These features are especially useful for JSON-like payloads and configuration schemas. They do not validate values at runtime. Use a validator when untrusted data crosses the boundary. The disjoint base decorator lets a framework state that subclasses from two decorated families cannot share a concrete type. That fact helps a type checker reason about identity, intersections, and pattern matching. The annotation is a promise from the hierarchy designer. If dynamic class construction, multiple inheritance, or registration violates the promise, static conclusions can become unsound. Apply it to deliberately separated families, not as a general optimization hint. PEP 791 introduces math.integer as a focused namespace for exact integer functions. Familiar operations such as greatest common divisor, least common multiple, integer square root, combinations, permutations, and factorial belong together conceptually and avoid floating point behavior. Existing imports need not change immediately. The new namespace is most valuable for discoverability and for APIs that want to signal an exact integer contract. Check the final documentation for transition guidance before enforcing one import style across a codebase. Unicode 17 updates character properties and names. The new grapheme iterator is more operationally significant because a user-perceived character can contain several code points joined by combining marks or joiners. Iterating by grapheme is useful for cursor movement, truncation, display cells, and text selection. It still does not solve typography or terminal width rules by itself. The XID helpers expose the properties used when judging whether a character can begin or continue an identifier. The tomlib parser gains support for TOML 1.1. This reduces the gap between Python and tools that emit the newer specification. A configuration format is an interoperability contract, so the reader is only one side of the decision. If files must also be consumed by Python 3.14, other languages, deployment agents, or editors, test those consumers before introducing 1.1 only syntax. Continue treating parsing as untrusted input handling, and validate the resulting data shape separately. Python 3.15 exposes additional controls for groups, ciphers, and signature algorithms through the SSL module. These are security policy surfaces, not tuning knobs to change casually. A stricter list can improve consistency and remove obsolete options, but it can also break older peers or platform-specific open SSL builds. Start from the organization's approved policy, test negotiation against representative servers and clients, and log failures in a way that distinguishes certificate, protocol, cipher, group, and signature mismatches. The threading module adds utilities for iterating concurrently, reducing the amount of queue and synchronization scaffolding applications must write. The precise API should be learned from the final library reference because concurrency details matter. Regardless of helper, test what happens when one iterator ends early, a worker raises, cancellation arrives, or the consumer stops reading. A shorter interface is valuable only when ownership and shutdown behavior remain explicit. Executable import lines inside path files are powerful but obscure. PEP 829 introduces start files as a dedicated package startup mechanism, separating executable behavior from path configuration. This makes startup hooks easier to discover, audit, and eventually control. Maintainers should inventory packages that write executable path lines, identify why the hook runs, and test the equivalent start file behavior. Avoid adding new executable path lines when the new mechanism is available. PEP 829 uses a multi-release transition rather than abruptly disabling a packaging technique. Python 3.15 introduces the alternative and gives installers, build backends, environment managers, and packages time to support it. The staged period extends through the releases leading to Python 3.20. Treat the dates as a program horizon. Discover dependencies now, migrate packages you control, and track the remaining transitive users. Consult the PEP for the exact behavior and warnings assigned to each release. PEP 803 establishes ABI3T, a stable application binary interface for free-threaded CPython. It is separate from ABI3 because the object model and compatibility assumptions differ when the global interpreter lock is absent. A project may therefore publish a version-specific wheel, an ABI3 wheel for conventional builds, an ABI3T wheel for free-threaded builds, or a deliberate subset. Packaging tags, build configuration, and test environments must agree on which binary is being produced and loaded. The ABI3T migration is not only a compiler flag. The how-to emphasizes opaque objects and supported accessor APIs rather than direct structure access. Free threading also exposes shared state assumptions that the global interpreter lock may have hidden. Audit globals, caches, reference ownership, callbacks, and third-party libraries. Build and import the resulting wheel on multiple supported versions, then run concurrency stress tests. A successful compile demonstrates syntax compatibility. Sustained tests demonstrate behavioral compatibility. PEP 793 introduces PyMod export to make extension module exports more declarative. Traditional initialization often consists of repeated creation, insertion, reference, and error handling steps. A structured export description can reduce boilerplate and make the module surface easier to inspect. Extension maintainers should evaluate the API where they already support Python 3.15 while keeping compatibility shims isolated for earlier versions. Review ownership and failure semantics carefully rather than assuming a shorter initializer removes all lifecycle responsibilities. PEP 820 adds a PySlot interface intended to replace patterns that depend on internal type layouts. Slots are the protocol hooks behind many Python operations, so a stable way to query and use them supports opaque objects and cross-version binaries. This is particularly relevant to ABI3T migration. Extension code should identify every direct slot or type field access, determine the supported replacement, and confirm that the replacement's lifetime and thread safety rules match the call site. PEP 788 addresses the difficult period when an interpreter is shutting down, but native threads, callbacks, or extension state may still be active. Safer finalization depends on recognizing that services and objects can disappear in an ordered teardown. Extensions should stop background work before finalization, avoid attaching threads late, and make cleanup idempotent. Tests should cover normal process exit, explicit embedding lifecycles, subinterpreters, and failures during module initialization. PEP 782 introduces PyBytes writer for incremental construction of byte strings. The pattern avoids repeated creation and concatenation when an extension emits a result in pieces. A writer also gives the API a clear finish or discard lifecycle. The code shown communicates the intended structure. Extension authors should use the final CAPI reference for exact names, signatures, and stable ABI availability. Benchmark with realistic chunk sizes and retain complete error handling for every append operation. A migration plan should include removals and deprecations, not only attractive features. The profile module now has a specific successor and removal horizon. Executable path file startup has a multi-release replacement. Native APIs continue moving away from exposed structures toward stable accessors. Run test suites with deprecation warnings visible. Convert actionable warnings into tracked issues, and make new warnings fail continuous integration. That keeps future upgrades from accumulating hidden work. Python 3.15 readiness crosses organizational boundaries. Application owners validate behavior and workload results. Library maintainers decide when new annotations and standard library dependencies fit their minimum version policy. Packaging owners track start files, installers, build backends, and wheel tags. Extension owners audit C interfaces and concurrency. Use one shared compatibility ledger so a passing application test is not mistaken for ecosystem readiness when a transitive wheel, build image, or type checker is still missing support. The release candidate is the right time to generate evidence, not to promise a universal deployment date. Add Python 3.15 to continuous integration, build or obtain required wheels, capture warnings, and profile representative workloads. After the final release, wait for the dependency and tooling set each service needs, then canary a controlled population with rollback criteria. Adopt new syntax and APIs selectively after the runtime upgrade is stable, so compatibility diagnoses is not mixed with broad source changes. These official sources define the typing, integer math, package startup, and integrated standard library changes covered in the first part of this chapter. The individual Python enhancement proposals provide normative semantics and compatibility reasoning. The library reference gives the callable surface for math.integer, while what's new collects Unicode, TOML, SSL, threading, removals, and other implementation details. Tool support may lag language acceptance, so check the release notes of the type checker and packaging tools used by the project. These official documents define the native extension changes, PEEP 803, and the migration how-to, explain the ABI3T target, opaque object model, and practical conversion work. PEP 793, PEP 820, PEP 788, and PEP 782 cover module exports, slot access, interpreter finalization, and incremental byte construction. CAPI names and availability can be precise and version-sensitive, so treat the final Python 3.15 CAPI reference as the implementation authority when converting production code. Python 3.15 is no longer a speculative feature list. Its release candidate establishes a stable feature and binary target, while the ecosystem finishes its own support. The strongest preparation is broad. Run the candidate, collect warnings, test encodings and imports, profile representative work, validate packages, and audit extensions. Adoption can then be selective. Use the new language, typing, library, profiling, packaging, and C interfaces, where they make intent clearer or remove custom machinery, and expand runtime changes only when measured evidence supports them.